After studying this module, you shall be able to know the importance of the orbital diagrams. Also, you will learn about the various configurations giving rise to the similar free ion terms. You will identify various features to be analyzed in an orbital diagram. Also, you will analyze various transitions taking place via the orbital diagram. Introduction. Now, first of all, we will have to understand that what is an orbital diagram. Orbital diagrams are a special class of correlation diagrams developed by Leslie E. Orgel. They are the diagrammatic representations of the electronic terms in reference to their relative energies with each other. In an orbital diagram, energy is represented on the x-axis and the vertical line in the center represents the gaseous ion in the absence of the ligand field with the delta value equal to 0. In these diagrams, only high spin, weak field cases are taken up graphically. This has been shown in figure. They are quantitative in nature and thus utilized in understanding the symmetry states of the highest spin multiplicity along with the observable spin allowed transitions. In the diagrams, the splitting for the dn is the same as for the dn plus 5 and opposite to that for d10 minus n, and both for octahedral and tetrahedral fields are readily seen on an orbital diagram. These diagrams are important in understanding the spectral, optical and magnetic properties of the transition metal complexes.
Now we are going to discuss the formation of high-spin complexes. The ligand field splitting parameter delta for high-spin complexes is quite small. As the value is small, therefore the electrons from the lower T2G level can easily migrate to the upper EG level in case of octahedral complexes, and hence pairing of electrons in the lower level does not take place, giving rise to the high spin complexes. Let us consider the case of Fe3 plus complexes with two different types of ligands, namely H2O and Cn negative. H2O is a weak field ligand in comparison to the Cn negative, which is very strong. Here we will have two different types of complexes as represented in the figure. With H2O as the ligand, the complex formed will be high spin with 5 unpaired electronic spins, whereas with Cn negative as the ligand, we get low spin complex with only one unpaired electron in the lower T2G level. Next, we are going to discuss the orbital diagrams in detail. Orbital diagrams are quite useful for the high spin cases of D1 to D9 electronic configurations in octahedral as well as tetrahedral field. For all the practical purpose, there can be two important orbital diagrams. Various concepts related to the orbital diagrams can be written in the form of various postulates. The first postulate says orbital diagrams include two sets of graphs which include all the high spin cases of octahedral and tetrahedral complexes. Orbital diagrams only cover the high spin cases. Orbital diagrams are only for the quantitative purpose. The following relationships are valid in case for the orbital diagrams. Dn and Dn plus 5 have the same diagram in the case of an octahedral field. Dn and Dn plus 5 have the same diagram for the tetrahedral field. Dn and Dn plus 5 in an octahedral field is reverse to that of Dn and Dn plus 5 for a tetrahedral field. Dn of the octahedral field is same as that of D10 minus n of the tetrahedral field. Dn of the tetrahedral field is same as that of D10 minus n of the octahedral field. Also, labels on the orgeal diagrams do not include spin multiplicity or the symmetry subscript labels for the octahedral cases, but we have to specify when we discuss electronic transitions for the complexes possessing center of symmetry. Next, we are going to discuss the orgeal diagram for the D1 octahedral case. If we consider D1 configuration as in the case of titanium 3 plus complex, it can be seen that the crystal field splitting will lead to lifting of the degeneracy of the 5d orbitals, and thus lower T2g level will now be occupied. It can be represented as T2g1 Eg0. When absorption of light occurs, the d electrons lying in the lower T2g level gets promoted to the higher Eg level, leading to a configurational change to T2g0 Eg1. The absorption of light and the corresponding change is shown in figure. The change in the configuration leads to a change in the term state of the system. For a free ion term, D1 configuration is fivefold degenerate since 5d orbitals are degenerate and a single electron can be placed in any of the 5d orbitals. Various possible configurations can be represented as dxy1 will be equal to dyz1 will be equal to dxz1 will again be equal to dx square y square 1 or dz square 1. The ground state free ion term for this configuration can be calculated as the total orbital angular momentum value capital L will be equal to 2 and the total spin quantum number will be equal to half with the spin multiplicity value of 2. Thus, the free ion ground state term for a D1 configuration will come out to be doublet D. In the presence of an octahedral ligand field, this free ion term for D1 configuration splits up to form new ground state and excited state terms. The splitting has been shown in the figure. The new ground state term is triply degenerate with the configuration T2G1 Eg0. Hence, the new ground state term can be designated as doublet T2G. The term is a doublet with the spin multiplicity of 2. When we talk about new excited state, the configuration is T2G0 Eg1. The new excited state term is a doubly degenerate doublet Eg level. Here again, the term is a doublet with a spin multiplicity of 2. The free ion term splitting can be represented as follows in figure. Energy difference between the two states is delta naught, which is energetically equal to the frequency of the absorption. In case of titanium 3 plus complex, this value of absorption frequency is equal to 20,000 centimeter inverse. D1 case in an octahedral field is similar to that of D6 octahedral as well as D4 and D9 tetrahedral cases. Entire framework of the configurations is represented by a single orgeal diagram since all of them will be having same ground and excited terms. The orgeal diagram for all these configurations can be represented in figures. On the left side is shown D1, D6 tetrahedral as well as D4 and D9 octahedral cases. On the right side is shown D1, D6 octahedral and D4, D9 tetrahedral cases, which will be having same orgeal representations. Left side of the orgeal diagram has E as the ground state and T2 as the excited state, whereas right side has T2 as the ground state and E as the excited state. Various configurations satisfying the right and left side of the orgeal diagram has been represented in the diagram shown. For the concerned transitions in all the cases shown, we have either the T2 to E level or from E to T2 level. No other type of transition is feasible. Absorption spectrum of the complex can be represented as an examination of the spectrum revealed that the band is actually splitted, or we can say that the main peak in the spectrum is also having a shoulder. The reason for this shoulder is the lifting of the degeneracy of EG and T2G levels due to the Jane-Taylor distortion. This again happens because of the unsymmetrical filling of the lower T2G level, which lifts up the degeneracy to bring stability in the system. Figure shows the absorption spectrum of the titanium complex along with a resolved absorption spectrum of the complex which has the shoulder. It can be seen that the absorption maxima is coming at 520 nanometer, which gives it a purple coloration. Next, we are going to discuss the orgeal diagram for the D2 octahedral case. D2 ground state configuration in an octahedral field can be represented as T2G2 EG0. Now, when the absorption of the light occurs, electron from the lower T2G level gets excited to the upper EG level. In case we are talking about a D2 case, splitting of the terms in an orgeal diagram is a bit complicated as compared to the D1 case, since here more triplet states are involved. The ground state term free ion term for this configuration can be calculated as follows. Total orbital angular momentum value capital L will be equal to 2 plus 1, giving the value 3. The total spin angular momentum value will be equal to 1, giving rise to the spin multiplicity of 3. Therefore, the new free ion ground state term for the D2 configuration comes out to be triplet F. After triplet F, the next higher term of same spin multiplicity is triplet P. Thus, for free ion terms, the triplet states involved are triplet F and triplet P. In case of an octahedral field, both free ion terms change their identity as triplet F changes as triplet A2G, triplet T1G and triplet T2G. The triplet P changes as triplet T1G. The two triplet T1G states are labeled as triplet T1G F and triplet T1G P in order to indicate the free ion terms from which they actually arise. The triplet states for the D2 case have their origin from the following electronic configurations shown in figure. A single orgeal diagram for a D2 case of an octahedral field is here to represent the entire framework of the configurations, since all of them will be having same ground and the excited state terms. The orgeal diagram for large number of configurations is represented in figure. The left side of the diagram is for D3 and D8 configuration in an octahedral field, as well as for the D2 and D7 case of the tetrahedral field. The right side comprises of D2 and D7 octahedral as well as D3 and D7 tetrahedral ligand field. The central vertical line is for the term without any field or free ion terms, represented as F as the ground state free ion term and P as the excited state of the lowest energy. From the diagram, an important observation can be made that the lines of T13F and T13P states curve away from each other due to the quantum mechanical non-crossing rule. Thus, the terms of same symmetry will never cross and will repel each other. Typically, three absorption bands can be observed in the spectrum of these complexes. For example, if we talk about D8 octahedral nickel complex, we typically observe three bands due to the following transitions, as can be shown in figure. The first absorption band is due to triplet A2G transition to triplet T1G-P. The second band is from triplet A2G to triplet T1G. The next transition is from triplet A2G to triplet T2G.
Summary. Orgel diagrams are a special class of correlation diagrams which diagrammatically represent the electronic terms N in reference to their relative energies with respect to each other. In an Orgel diagram, energy is represented on the x-axis and the vertical line in the center of the diagram represents the gaseous ion where there is no ligand field presence. That is, the value of delta will be equal to 0. The Orgel diagrams are important in understanding the spectral, optical and magnetic properties of the transition metal complexes. Orgel diagrams cover only the high spin cases. In presence of an octahedral ligand field, the free ion term for the D1 configuration gets split up to form new ground state and excited state terms. Capital A is there to the entire framework of the configurations which are represented by a single Orgel diagrams since all of them have same ground and excited state terms. The lines of T1G capital F and T1G capital P states curve away from each other due to quantum mechanical non-crossing rule in the Orgel diagram for the D2 configuration. Thus, the terms of same symmetry will never cross and will repel each other.